Hi, today I'm with Emilio, a final year PhD student in the Foundational AI CDT at UCL, studying neural operators. Thanks for coming on, Emilio.
Of course, thanks for having me.
So before we dig into what exactly a neural operator is, let's first go to what problem it's trying to solve. So as I understand it, it's trying to solve differential equations efficiently. Is that right?
Yeah, I mean, as I've gone through my PhD, I think I sort of matured my understanding of it. But I guess I'll start with like the original paper or the original idea. So the original idea is, um, if you go back to 2014, 2015, people are trying to solve PDEs using effectively CNNs, right?
Hmm.
So if you've heard of the UNet architecture, this is originally an image segmenter, but then very quickly gets used to solve like uniform grid PD problems. And they're fairly good, but they're really parameter intensive, and they are fixed to the resolution that you trained on. So if you trained on 120 by 128, that is the resolution you are fixed at. There's no way that you can do up or down sampling before it as like an additional pipeline, but the architecture itself is fixed. Um, and so the idea behind neural operators is, well, let's try like it's kind of an accounting trick. The idea is like let's try to map, like let's try to consider the pixels, the points, as like sample points of a continuous function, and then how can we learn? How can we make an architecture that goes from the some sample points to some other sample points?
So, what kind of PD or differential equation would you be trying to solve in the first place?
I mean, any effectively, like any you have data for, you could
Hmm.
solve. So I think like the original ones for heat, like the heat equation, something maybe a bit more modern that maybe more people be more aware of are like diffusion models. They have like a, they solve this diffusion equation, and most of them usually have like a unit somewhere, and it's effectively sort of doing this like solving in some sense.
Hmm.
But it's basically for any PD. My domain is in like wave equations and acoustics and stuff, but any physical process that has a PD underlying it, you can use in theory neural operators to solve them.
And you're also connected to the medical department, is that right?
My supervisor is in the medical department. I don't think I've ever seen a medical image in my entire PhD. Um, but yeah, my supervisors are primarily medical imaging people. The original idea for my PhD was to create like an inverse solver. But who would have thought making new neural operators would be difficult? Not me. When I was like 18 or I guess 24.
So there's these scans, it's like scans of the brain, but you can only sense it on the skull. And what's the differential equation being solved there?
Um, so that's I think ECG, EEG. Those ones. So like, if you were to write out like the biophysical thing, like the actual biophysical PD, it'd be really hard and probably intractable.
Hmm.
So like this is where the idea of like this is where the abstraction of neural operators can be useful. If you can define an operator between two like vector spaces, for example, um, you can like you don't really need to know the underlying physics beneath it. You can just sort of like if you have enough data, like this is a deep learning paradigm, right? If you have enough data, you can just learn a good enough approximation and hope it generalizes.
I see. So traditionally you would have like a fixed, suppose you're doing some numerical method to solve a PDE. You would have a
Yeah.
fixed PDE and you would try and solve it or like propagate it forward in time. Whereas in
Mhm.
your case, it's like the PDE is actually super complicated underlying the behavior in the brain or whatever, but you don't
Mhm.
even need to know it. You just need to know how to solve it or what the solutions look like.
I mean, like in theory, right? Obviously, practice it gets a little more difficult. Because like in general, I think in mathematics you get this like axis of applicability, like power and like generalizability. Um, so like the F of t, for example, really powerful, ubiquitous everywhere, brittle. The moment you get off uniform grid sampling, it just completely breaks down. So
Hmm.
like, um, and the same sort of true in PD solving. Like you can either put a lot of like mental work into getting a really fast solver that gets to machine precision for every single point, but you basically need to know like the full like spectral characteristics of your PDE, which is like really hard.
Hmm.
Let alone for problems where you can't necessarily where you like know a PDE exists in theory, but you maybe don't necessarily know the closed form of it, which is actually fairly common. Um, so
The
like
closed form of the PDE or the solution to the PDE?
the solution is almost very rarely closed form. Sometimes you do know the sometimes you do know, and most derived PDEs obviously have a closed form. But if you're like, okay, from the electrical like the electrical conductivity or impedance, whatever they measure it, like at my skull, how that relates to like my hippocampus firing, like there exists a physical PDE you could probably in theory write out. And maybe someone has, but as far as I'm aware, I'm not aware of it. And so I don't think it's like the idea, like one of the ideas behind neural operators is like, oh, we can help accelerate science, for example. Like the CERN has a ton of data, and maybe we can learn some new PDEs about physics from the data. Um,
Mm.
so this is like one of the ideas that this would be useful for. Um, but yeah, but like primarily it's usually solved for PDEs we have closed form solutions for, but we want to like accelerate because obviously the only it's machine learning architecture, so the only way to train it is by having data. And obviously, if you have the closed form PDE, like if you know what it is, you can use an expensive solver to generate lots of data, and then train a model that's much faster and cheaper.
Yeah.
Which is primarily what I do. But in theory, this could be extended further. But I've not really seen many people do work on this, or like they usually, yeah, I've not seen many people do work on this. I've seen some people sort of go around it, but it's usually for um, like it's usually for like efficiencies of like blades in like a specific kind of fluid, which like the PDE would be coupled and very complicated, and they sort of don't even care about the PDE.
Hmm.
But I've not seen anyone like discover new physics from neural operators yet. I don't think they're not at that level of precision.
Okay. Okay. So the let's suppose for the moment that we do know what the PDE is and we're trying to solve it.
Hmm.
Then there's
Yeah.
a few methods I was aware of before I came across your work and your field. So one was
Hmm.
like you analytically solve it, like with pen and paper, you find out some closed form solution for the
Hmm.
PDE. And that's the first method you're told, and then you're told, oh, actually, that barely ever works. You can almost
Yeah.
never do that. And then the next method you learn is a computational method of
Hmm.
like you take the initial conditions and then you discretize your space and time, and then you do tiny steps in time to evolve the initial solution forwards.
Yeah.
And that can work, but you require a really fine discretization, both in space and time, in order to get reliable propagations of the initial conditions. So that takes a huge amount of computational power, and also you can't change the resolution afterwards. So in this method, you're imagining the function as a kind of a giant vector, a giant sequence of numbers in this grid
Hmm.
on the space. Whereas what's really going on with a PDE is you want a function, and you want to be able to represent a function and make transformations on a function. And so neural
Hmm.
operators give you a way to do this, right? To like start with a function that's the initial condition and then evolve it forward in time.
Yeah. I mean, I guess I'd be hesitant like call it a like it's a vector still because these had to fit in, like you have a feature vector of 128 by like 128, right? So like you it's still compressed to a vector,
Mm,
but yeah, the idea is really similar to these like numerical method techniques where you have like um some solver that does like that takes in all the mesh points, or I guess free space points if you're doing like a point cloud, um and then applies like then you have the initial condition over that and you apply the neural operator to that and it propagates forward.
mhm,
um
mhm.
of course you also have not to muddy the waters, but you also have time harmonic and time dependent PDEs, which are different. So the time harmonic ones you don't need to time step, and
Okay.
the time dependent ones you do, but that's neither here nor there.
So then, yeah, I see. So you can't actually fit a function on a computer. You see, you can only fit finite representations on a computer.
Yeah.
it is still going to be parameterized by some finite collection of numbers. Um,
Mhm.
but like in these previous computational methods, it really would just be like a grid of values. Whereas now you're doing some more abstract representation, like the Fourier transform representation or something.
Yeah, so the method you're talking about is called like there are lots of them that are very similar, but the one that comes to mind, probably the one you're thinking of, is called FEM. It's the finite element method, and FEM's really powerful. For linear PDEs, using FEM you can effectively solve any linear PDEs, and there are some really good methods to solve non-linear PDEs. They're obviously much harder because our theory is like, well, less developed, but like there are still pretty good approximations you can do using FEM or FEM adjacent solvers. The issue with FEM is twofold, as you sort of mentioned. One is that for a fixed PDE, one solver is equal to one fixed PDE, which is like fine on the face of it. But if you think about, oh, actually, all the like parameters of the PDE, like the diffusion coefficient or like the speed of sound or you know the permittivity and of like space or whatever, like
Hmm.
these are all like, and if these are constants, that's fine. But if and like especially they're physical constants, but if they vary over space, which most things in life do, then for every kind of function that describes like a parameter of the PDE, you need to do a completely different solve, and you don't get to reuse any of that computation.
Right.
Which is like the first big reason why neural operators like are a little better, and the second reason is that, as you sort of say, it's fixed to the grid you solve on.
Hmm.
Like you can in like, and so each mesh, which is like a bunch of grid points, um, each mesh is fixed. So if you want to do a different mesh, you need to regenerate the mesh and then do the solve. Like, and then to carry out both of these, there are ways you can make this more efficient, right? Like the field of numerical analysis is basically as old as computing, so there's lots of very smart ways to do very smart things. But in general, you need to have a lot of expertise and knowledge of your PDE and or your domain. Um, Otherwise, as you say, it's really intractable. You're doing like a really high resolution solve, and if you make very minor adjustments, you need to completely redo the solve. So it's not really reusable in the same way that like a lot of other computation is.
I see. So with neural operators, you could have not just a mesh, but some arbitrary sample of points that you
Mhm.
measure the function at, and you train your neural operator on, and then you could generalize, or hopefully it can generalize to any other set of points. So it could predict the function at a future time on some other grid of points, or some other mesh, or just some arbitrary points in general. Is that right?
Yeah, well, small caveat here is that like yes with an asterisk, which I'm sure we'll get to in a bit. Um, but yeah, the two like the two draws of neural operators are using traditional methods. Because remember, traditional methods you get machine precision on every single point, so that's a really high bar. So like if you so for traditional methods, for neural operators, the big draw is one, you can train on different PDE, like if it's the same, like it's the heat equation, but you can use a different diffusion thing, and you as long as you have some way to encode that
I
that
see.
change of variable into your architecture, either as input or like something more parametric, um, then yeah, you then in theory you can train one solver to solve all these coupled related problems. And then, as you said, with the asterisk, is that this can also generalize to different points or different resolutions. So
Hmm.
that those are usually the two draw, and obviously it's much faster because once you have it solved, then it's just a bunch of linear. There's a bunch of like faster linear algebra as opposed to having millions and millions of points. And obviously, if you do inverse problems, which I don't think we're going to get into, but if you do inverse problems, then it gets even better because inverse problems are much nicer, or they're a lot more coupled, and the inverse problems are usually ill-posed, so you can't normally solve them analytically or even in a closed form way. So, or in a experimental way, it's usually a lot harder.
So an inverse problem is when you're given like the boundary conditions and you want to find the rest of the solution.
No, that's also for a problem. It depends on the problem. But my,
Okay.
my favorite my favorite inverse problem, I think it was the title of a paper I got told in my second year of university, was can you hear the shape of a drum?
Okay, so you're trying to go from sounds to shape.
Yeah, right. Because obviously, like the way it like resonates inside is indicative of the shape, and so the idea of this paper was like, okay, if you have a bunch of different drum like hits, can you actually tell what shape each of them are? And the answer is yes, but it's hard. But that's like the idea of an inverse problem, or like in a more medical field, if you're doing like an ultrasound, it's kind of like an inverse problem. Which if you have like the old like the traditional style sensor, it's just time of flight, which is a very easy inverse problem. But if you're doing like a breast ultrasound or a brain ultrasound, which is like sort of both being developed now, you can't just do time of flight because the brain scatters, like these things will scatter off the sound everywhere. So then you have to like measure the entire like sound wave and then reconstruct the path that it went. This is actually what ray tracing was originally invented for. So
With this time of flight thing, you're saying like you get some signal at the surface of the skull, and you're trying to tell where in the brain that signal came from, and you can't just say, "Oh, it took 3 milliseconds to arrive here and 2 milliseconds to arrive here," and then triangulate, because the speed at which the wave propagates it varies through the brain and through the skull.
I mean, it does, but the biggest issue is that if you have like a traditional transducer, so if you've ever been to like like got an ultrasound at a hospital, it's like that, like the stuff they use for like pregnancy tests, is
Hmm.
it's just one. You can think of it effectively as like one speaker, and that's
Hmm.
pressed against your skin, and so you can just measure like you know where the source is, so you can just measure the time it took for you to get the pulse back. But if you have like something around your breast or your head, for example, and you have like 300, 400 transducers, then you don't know necessarily which signal came from where. And if you just did one at a time, you wouldn't really get a big picture because most of the energy would be reflected or scattered off somewhere. So you wouldn't actually be able to like. It'd be very unlikely that if you put a source here, you'd get much signal from the back of your head. So
I
you kind of
see.
need like a whole dome. And so when you have a whole dome, then you have coupled sources, and that gets a lot harder because then which source did it come from? And then doing time of flight's harder because like if you could somehow color each wave, then you could maybe do it. But like that's not how physics works. So you have to do some reconstruction, and then you know, did it come from a closer source or a further source further or a source further away, and didn't get scattered. So
Mm.
yeah, it's inverse problems are really hard, and they're ill posed, which means you don't even get the nicety of like knowing that the problem is well formulated because you actually have more unknowns than you have knowns. So it's a very hard field that I'm sad I didn't get into, but also kind of glad I didn't because it's really stressful.
So it's an inverse problem in the sense that there's structure within the body that's modifying these signals.
Hmm.
That's the way the causation goes, right? The structure in the brain causes the modification in the signals, which you then receive. And we're trying
Yeah,
to go in the inverse direction. Given these modified signals, let's infer what the structure is that caused them.
yeah, yeah. Effectively,
Okay.
like if you want to in terms of operators, then you have a forward operator, which is like source to target, and
Hmm.
then via like the medium, and then the
Hmm.
inverse problem is you like do the adjoint and you do the inverse, where you're trying to where you have the source and the medium, so you have the source and the final solution, but you don't have the intermediate like material, and so you try to reconstruct what the material looks like.
Hmm. So, like, maybe this isn't specifically what you work on, but the general field of neural operators, one part of it is trying to efficiently reconstruct brain images from brain scans.
Yeah, so like I've talked to some people who do like neural operators on MRIs and stuff like
Hmm.
that to try and where you can use like low resolution images and sort of like you can use like fewer high resolution images and then more low resolution images and try to do some like fancy interpolation using like a neural operator.
Hmm.
Um
Hmm.
and so that's definitely a like a big field of it. But I think that's still quite new, but just because you don't have the sort of bounds and confidences on your lower praises that you maybe do have in of traditional methods. And MRIs are really expensive as already as well, so you can kind of you can assume there's at least some compute to do to do this inverse problem. Um, but yeah, like it's still an up and coming field, but like I like the stuff I'm aware of is for ultrasound, where like if you want to do these inverse rate things, you need like a supercomputer effectively, or maybe like a few like RTXs. But the idea is like, oh, can we get down to one? Like, can we do this on a computer that like a doctor may actually have under their desk? Um,
Right.
because and that's all the and then also ultrasound is a higher signal has a lower signal to noise ratio, so your model needs to be less good because you have intrinsic errors greater from the actual sensors.
Hmm.
But yeah, like inverse problems are definitely a big field of it. It's not something I've sort of gone much into, but I am aware this is like a big component of neural operators. But the stuff I primarily do is like the forward operator, like going from initial conditions to the final condition.
I see.
Um,
So this would be more like you've got this setup of you've got a I don't know, some material that's hot in some places and cold in others, and you want to see what it's going to look like in an hour.
yeah. Um, Also, I mainly do wave propagation, so I have like a bunch of sources, and I have the material, the domain, and then what does the final like wave look like?
Hmm.
And that's usually the sort of stuff I'm doing. But like that comes up in like lots of places. So like some way that might like so if you think of like fluid modeling, right? Or the modeling of like aircraft or like services of aircraft stuff like that, those are mainly forward problems because you have the CAD file for the airplane and you know where the wind's coming from. You want to make sure it has all these aerodynamic properties. So like image problems are definitely like in some sense sexier because like you're doing a reconstruction and you're discovering hidden information. Um, but like forward problems are still really useful. And they're the ones that are primarily used a lot. So like simulations are all forward problems. So if you want to like simulate the weather, you're doing a forward problem. You have some initial condition, guessed initial conditions, and you know what the topology of the Earth looks like, and then you try to predict what's going to be in the future. So like forward problems are like are if anything probably a little more ubiquitous just because they're usually easy to solve. But they're also in the sense that like it's easier because we have all these we have like 70 years of numerical analysis to tooling to try and solve them with AMS problems. Machine learning seems to be doing a little bit better of them because you don't need to worry about how to even formulate the problem itself. If you have enough data and you have a good enough regularizer, you can just sort of like hope and pray, and it usually works out.
So what I was trying to understand what a neural operator was. And
Mhm.
let me run by this by you. The idea I came across was an an ordinary neural network takes in a vector and outputs a vector, and in
Mhm.
between it applies sequentially a bunch of transformations to transform this vector into other vectors, eventually to the output vector. And it usually alternates between linear and nonlinear transformations. And then a neural operator is like an analogy of this, where instead of having as input a vector, you have as input a function, or you would just call it a vector still because you're a mathematician. It lives in a vector space, which is a function space, and it outputs a function, and then it applies a sequence of transformations again, alternating between linear and nonlinear, but this time these transformations operate on functions rather than vectors. Was that
Yeah.
correct, what I read?
Yeah, like that's yeah, effectively. I guess if you want to use like more like abstract jargon, you can think of them as like sequence to sequence models. So you have like if you have a sequence of source points, and you try to, and then like each of the linear layers is like a sequence to sequence like operator that goes from one sequence to the next sequence either in time or as like a hidden latent state, and you go all the way through until you reach the end. Um, so like that's maybe more of a more praxis way of thinking about it, but like effectively, yeah, it's like you replace the um like the way I think about it is that if MLPs or DNNs, whatever you want to call them, are like functions, then neural operators are shockingly operators. So a function works on has one specific input and gives you one output, while one operator is it goes from like a more broad class. So like yeah, like the analogy I think is clearer on paper. At least in my head, but maybe it's hard for me to explain. But like a function takes a scalar, gives you another scalar. And then a operator gives you like goes from a vector to a vector. And so the same sort of like level of abstraction works where an MLP is takes one vector to one vector, and operator takes a bunch of points to another bunch of points.
Okay. So there's uh yeah, okay. So then how are you we touched on this briefly already, but like how are you representing these functions or how did you choose to represent your functions in your work?
Um, so in my work, I just treat them as a tensor. I think that's fairly standard. Usually the crux of difficulty comes in how you do like the spatial mixing of all the points, right? Like how do you, if you have like, let's just go back to uniform grid for this for the sake of it for now, and we'll go to non-uniform grids because they're a little bit harder. But if you're on a uniform grid of an arbitrary size, like you have you have n squared points,
Hmm.
and so the idea is like how do you mix all those points together to get either the next time step or the next the next hidden step, right?
Hmm.
Um, and so obviously, I think if we go back to what I was saying in the very, very beginning, UNets were for this. So you sort of compress, you do a CNN of all of them, and you keep applying CNNs until you get to some small latent dimension, and then you undo all the CNNs.
Hmm.
But as I sort of mentioned, that's really brittle. It's really dependent on the initial, like it's fixed on that discretization, or if again we're on uniform grid, so it's fixed on that resolution. And also it's really parameter inefficient, right? I don't know if you ever use CNNs, but like you have a high have a high feature space or feature dimension, and then all of a sudden you go from if you're doing a 3 by 3, that's 9 times that's like 9 times the number of parameters that you would expect from just like a single
Right.
weight matrix. So like they're really inefficient in terms of parameters. And so I guess I'll give you more the history of that if that's okay. So like so then the first thing comes in is the FNO, and this is like the gold standard. It's the one basically everyone still uses, primarily because it's conceptually really simple and also really easy to implement.
For knows the Fourier neural operator.
Yeah, the Fourier neural operator. And so the way the Fourier neural operator works, um, is it so as long as you have a uniform grid, it takes the FFT, the fast Fourier transform of this uniform grid, which gives you its spectrum. And then it's like a regularizer. It basically drops all the higher order terms. So you have like some hyperparameter, which indicates how many modes you care about. And then you drop all the ones you don't, which makes your space like a really small latent space.
Hmm.
And then you do like some dense kernel over that. So you actually do a tensor. So it's not even so the FNO actually uses like a proper tensor. It doesn't use like I mean, I guess you could say it flattens it and then does an MLP or whatever, but like traditionally just use an actual a dense tensor. You apply that to like the little spectrum that's left. You undo the FFT and then add a residual, and then
Okay.
either have like and not then have like a MLP at the end or just a non-linearity, whatever you want. But like that's the key idea is that you do this bandwidth limiting component, and then you have this residual which keeps all the high frequency components in, and then you have some sort of
Ah.
feature mixer. But the great thing about this is that that this works on any resolution within in theory. Like you need to have enough. The resolution needs to be high enough that this like bandwidth limited section has all non-zero frequencies. So if you trained on like 32 by 32, you couldn't really do 16 by 16, because like you just wouldn't have enough features. Like your model will get very confused. It'd be out of distribution. But if you trained on like 64 by 64, you could in theory evaluate on 256 by 256, because this bandwidth limiting means that is this regularization means that you can, as long as you have more points than the number of modes the model's expecting, it will still work. And so you get this like cool generalizability and like this one shot super resolution, all the great buzzwords. You get all these out from them, and obviously depending on the problem, these either work really well or don't.
You can go to higher resolution, but not to lower resolution.
Yeah, I mean, obviously, if you could do low resolution by just averaging all the pixels together, which is
Ah,
so
okay.
going
Okay.
down is usually pretty easy,
Yeah.
which is why it's not usually considered a problem. But that is like a technical thing. If you did trained it on 64 by 64, then and you evaluate it on 30 by 32, then like obviously the bandwidth limiting is going to have some like pixelation. Um,
Hmm.
but yeah, like in general, you can train it on any resolution and evaluate it on it. You can train it on some fixed set of resolutions and evaluate it on any resolution, and that's like the core conceit.
And the training part means like you're doing the fast Fourier transform, and then
Mhm.
you have some convolutional layers on that representation. Is that what
No,
you
no,
said?
no. You do the fast Fourier transform, which gives you the spectrum.
Yeah.
Um, and then you drop all the modes above above and below some like high parameter limit. Usually it's like 12 or 16.
And
Um,
that corresponds to throwing away high frequencies.
yeah, effectively.
Okay.
Um, and then you literally just do a tensor. So so if you do have 2D image, you have the real component, the complex component, and you have each of those for every single feature.
Hmm.
So you have like this cube almost of like values, and so then you do a tensor operation between some learned tensor, and then you undo the FFT to get back to image space, add your residual image, and then some nonlinearity or whatever, FNN or whatever you want.
Okay, so training means tuning the parameters of that tensor and also the nonlinear like MLP layer you do after that.
Yeah, effectively. That's basically exactly what the Yep. This is why it's really simple. It's like you can literally implement it in 30 lines of code.
Okay.
As long as you have an FFT library.
And then the training data would be you would need some kind of actual data of actual waves moving or like a numerical solver that propagates it forward, and then you'd use this as your training data.
Yeah. Yeah, basically. I use simulated data just because it's easier than getting like try recording 1,000 different recordings. It's a nightmare.
Yeah.
Um, but yeah, like if you were like a mining company, right, and you did a bunch of seismic like testing to try find for oil, and you had that data, then you could use that data, for example.
Hmm.
But yeah, this is the FNO. It's really good. It's really ubiquitous and really powerful. But to the keen-eyed or listeners amongst us, you'll sort of pick up like the two difficulties of this. One, you need a uniform grid. Because if you step off a uniform grid, you can't use the FFT anymore. So the core idea of the FNO will still work, but all of a sudden you go down from ON complexity to n squared, or maybe n log n if you're really really fancy. But you have to do this the non uniform Fourier transform, which is really hard and kind of still an open problem. And then the second issue, which is more specific for my problems or for problems that have like waves in them, is you're doing this bandwidth limiting. So you're like obviously because you have the residual connection, and then the feature mixer like the MLP, like you incorporate the higher frequencies in, still, but like you're still fundamentally doing this bandwidth limiting.
Hmm.
So there is like still like you can think of it as like a low rank um operator over all the like if you want to think of it in terms of mathematically, it's like you're doing a low rank operator over your function, where you're convolving with a low rank operator. So even if you're doing a bunch of like feature mixing that you do with like the MLPs and stuff, you still unfortunately have the issue that if you just need more frequencies, the FNO is not really going to be able to see them, or not see them well enough. And the FNO, and at least in its original implementations, it can be really parameter hungry. So like as you increase the feature dimension and the number of modes you keep, like you can easily get to like 8 million parameters, like with only having 4 layers. So like it can really scale up really, really quickly.
The high frequency parts, they do get through. They don't get zeroed out completely because they go through the residual
Yeah.
layer, but they get transformed in a different way. It's like the MLP has to figure out how to update the low frequency
Yeah,
waves.
I mean, you can think of them like if you want to think of them like the Fourier basis, like if your input vectors are all Fourier coefficients, right? Then like the residual connection mixes up the Fourier coefficients, even in the bandwidth limited kernel, you're still seeing some high frequency components, but you're just not seeing many of them. The rank is really low.
Hmm.
So like it's not that you don't see high frequency components, which is a misconception I had when I started, because you do see them. It's just that if you're doing problems where their high frequency component is like a non-zero, where it's not so you can just like do some minor tweaking on, where like you're doing some sort of beam focusing, and so like the high frequency modes are really really important, because they actually contribute substantively to like the actual output. Then the FNO is just going to struggle, because like even though it is seeing these high frequency components, it's not really able to do the low rankedness sort of gets in the way. Um, so
Mhm.
so it's more about it's more an issue about rank rather than specifically the frequencies, but um, in practice it comes out to be the frequencies because you're doing a bandwidth limiting function. But like yeah, it's there is the high frequencies are maintained and they even get like played around with a little bit, even in the spatial mixing component. But the biggest issue is that they just don't like you just the kernel's too small. You really just can't do enough spatial mixing because you're having some like assumption there that's just getting in the way. Mhm.
Okay, so that was the FNO, and its two problems were you fixed to your grid that you
Mhm.
train on, um, or you're fixed. Sorry,
You fix to a uniform grid.
yeah, yeah, okay. And then the other problem was you are throwing away or losing information about how to update high frequencies.
Yeah.
So what's next in the story?
Well, I mean, that's where my research comes in. Hopefully, fingers crossed. You know, who knows? I'll answer the uniform grid question, then go into the high frequencies because the high frequency is more specific to me. I'm not the only person to figure out to do non-uniform grids.
Hmm.
Um, but so non-uniform grids, as I sort of mentioned earlier, you can think of these like if you have all these sample points, you can think of it as a sequence of sequence problem. So probably people are screaming out attention, and you're right, attention is great. Who doesn't love some good attention? Um, so the when essentially needs come when like transformers are sort of really getting into their prime 2021 2021 this is where people start talking like you see some discussion of like using either vision transformers or which sort of have the same issue because they're on a uniform grid again kind of or just transformers directly on the points and this is like usually how you get around the uniform grid is there's like two schools of thought. One of them is you use like a transformer or some other architecture like a state space model or something like that. Use that to map from your grid points, interpolate them in effect onto like a uniform grid, and then do the FNO on this latent uniform grid. Um, and that's like sort of like the some of the original ideas behind this sort of stuff is like, oh, how could we do like FNO manifolds? And the idea is like, oh, you project a uniform grid, do the FNO on this uniform grid, then project back.
So you have a sample of points,
Yeah.
and then you draw a grid that covers all of those points, and then you guess the values of all the other. You were going to jump in. I said it wrong already.
Yeah, no, I was gonna say that you don't you it's more that you in the same way that like a autoencoder learns like a latent space, and the latent space isn't like physical; it's like more
I see.
conceptual. The same sort of idea applies. So you don't project down a uniform grid. You
Hmm.
more take all the points and then like interpolate to like a latent uniform grid in some like you know feature space somewhere else, and then you do the
Okay.
FNO on that. Um,
Okay. So then the points on that grid, that latent grid, they're not going to obey the wave equation. Uh, you,
yeah,
they'll obey some other equation. And this is
yeah.
why you need some very general tool like the FNO in order to learn that mapping.
Exactly, yeah. And this works kind of well, but doesn't really work super well.
Hmm.
Um, like I'm not sort of gonna get into it, but like the key issue is that like as you sort of said, like the PDE or the operator on that on the latent space isn't necessarily the same operator you want, and
Hmm.
like you're getting like some sort of like interpolation error from going from your grid from going from your point cloud to this uniform latent grid. So you get so you get an error there. And then some people are like, okay, cool. And so the second camp is like, let's just ignore the FNO. Let's just do something else. So for example, let's just do straight transformers. We don't need anything else. Transformers are all you need. Just go straight ahead. Which works great until you reach the issue that everyone who does transformers has reached, which is that it's quadratic in terms of memory and time. Time's less of an issue, but the memory is a huge issue. So, you know, 64 by 64, like 120 by 128, which is still fairly pixely, 16,000 points. And if you have like 5, 6 layers, God help you. And you have to remember that like scientific high performance computing or scientific computing your the number of points you have are in the order of millions, if not like if you're doing the really like universe simulating ones, like something to have 1 billion points. So like attention just ain't gonna cut it. Like there's no like Google has spent God knows how much money, like OpenAI has so God knows how much money to make a context length 1 million, and that's
Right.
taken us to like basically the end of last year. So like ain't gonna work. So then you sort of go into like a linear attention method. Um, some people have sort of done the vision transformer idea of like you project a smaller subspace of all your points, so some sort of grouped subspace of all your points, and then you do attention on that. Some people just like let's just straight up just use linear attention, which also kind of works well. Um, so yeah, so the two ways to sort of get around it are using, the sort of latent uniform space idea, or basically a graph neural network. I mean, transformers are graph neural networks. Don't at me, but like yeah, you either have a graph or you project to a uniform grid and then use the FNO. And both these ideas are problems.
So these are two existing methods to go to deal with non-uniform grids. And
Yeah, I
then
mean, the second is more like a family of methods. Like, there's a bunch of different papers about like uniform grids using like linear attention or whatever.
mm,
But yeah, these are the sort of two main camps. Is either you just treat it as a point cloud or you use a latent space trick. Um, and so the idea that I had, well, the idea my supervisor and I had, was like, why throw the baby out of the bathwater? Like we have these 70, 80 years of numerical analysis where people have developed like algorithms to solve these exact problems.
mhm.
Why don't we just adapt one for like, the deep learning world, right? Like why reinvent the wheel? So the algorithm that we chose is called the fast multiple method, or the FMM. Um, and it's a bit complicated.
So the first multipole method is an existing method in
Yeah.
numerical analysis, and you sort of
Mhm.
made a neural operator that emulates it.
Yeah. I guess in like some jargon, we we use the information flow of the FML algorithm as like an inductive prior for our architecture.
Okay.
Um, yeah. But more practically, I guess like what we do is we eat the FMM algorithm is sort of broken up into like lots of different stages, which each stage having like an operator which derived from your Green's function. So you have these operators which derived from like your interaction kernel, um, and the sort of super high level idea that we sort of had is why not replace all these operators that are derived from the Green's function or the interaction kernel and just learn them directly. And that was
Mhm.
like the first that was like the 2.5 years of my life just sort of getting that to work. Um, but yeah, like that's like the core conceit is that why not let the really smart people who made up these algorithms like keep their work? Like why do all the work of like how to sample points and group points together and approximate stuff? Why not you leverage all that knowledge, and then replace the part that machine learning is actually really good at, which is approximating complex operators. um, and so that's basically it. It's like it's we replace the operators from the FMM with learnable components and then use the FMM to do everything else.
I see. So you're keeping like the structure of how information flows
Yeah.
through the algorithm and representing that and as a neural operator. But
Mhm.
some of the actual transformations that occur, instead of being derived from a Green's function or whatever, is instead learned.
Yeah, effectively. That's exactly what we do. Yeah.
Okay. So then, like, what are you losing by throwing away that Green's function? And what are you gaining?
Um, well, you lose like the exact solution, right? Like if you the FMM is used to solve like n-body problems in physics and electrostatics. So like
Mm,
if you've seen the really cool physics universe simulations, those are like they don't use the exact FMM, they use like an FMM plus an adaptive grid method, which I'm not going to get into because it's really complicated and I barely understand it. But like it's effectively a precursor to the modern billion point simulations we use now. So if you don't have the exact green function, you do lose some accuracy, right?
Hmm.
I mean, you only lose some accuracy because the FMM is already approximation, but you lose even more accuracy because you're learning from data, and so you just don't get the same level of fidelity that you would uh, if you had the exact greens function. But the benefit is to be a neural operator. Um, like the FMM is specifically designed for free space, so there's no difference in conductivity, or there's no difference in gravitational field anywhere. Which is good for the problems they're designed to solve, but for problems in like wave propagation in human tissue, for example, it's a lot harder because the speed of sound changes over the body, or even if you're doing something like more toy where you have like a scattering object in the middle, um, if you send waves through that, it's the speed of sound changes and you get the scattering pattern. So like the benefit is that we get to be a neural operator and we get to learn all the stuff from data, but obviously the downside is that we have less like we it's unclear how much of the bounds we get to keep from the FMM, if any. My instinct is probably not many.
When you do the FMM with the greens function,
Mhm.
I think you once described the greens function as like a key that allows you to unlock the solution. It's like you get an initial condition, and then you do some magic with the greens function to it, and then you get the evolved state.
Yeah, so if you do some like LPDE theory or some like advanced function analysis, basically, so for a given PDE, for fixed parameters, keep in mind. So this is another reason why I can't really use the straight FMM is you have to like learn component is is that for a given parameter of your PDE, so like the speed of sound being some fixed map,
Mhm.
um, the Green's function is like the fundamental solution. It's technically the fundamental solution with boundary conditions, but not sort of going to get into the nuanced difference between those two things. But it's basically the fundamental solution. Um, and so when you have another initial condition, so if you have if you have the PDE with respect to U here, it's equal to some driving force F on the right hand side.
Yeah,
Um, the fundamental solution corresponds to the solution of the PDE. And so if you want to solve the PDE for a different driving function, all you need to do is convolve it with your Green's function, and that's it. Then you get the
I see.
solution. So this is the reason. This is the reason why linear PDEs are like effectively solved mathematically. Not really, but kind of solved mathematically, is because you have this Green function. Um, if you do optimal transport, it's like the transport coefficients kind of like the Green's function is a very old theory that's like is ubiquitous in a lot of modern mathematics now. But yeah, it's basically the Gram matrix, the pairwise interaction strength. It defines the interaction between any 2 points in space.
So um so the greens function is the solution to the homogeneous PDE, and then
Yeah,
in order to get the solution to any non-homogeneous version of the same PDE, you just convolve the greens function with the driving force F.
yeah,
Okay.
exactly. This is the reason that's super useful. Is because if you have the Green's function, then you don't need meshes, you don't need anything. You can just analytically solve
Mm.
at any point you want.
Hmm.
Obviously, really hard, but
Okay. So then like the FMO F no FMM. So the
mhm.
FMM will work provided you have the greens function, but then for the
Yeah.
human body, the greens function, even getting that is going to be ridiculously hard, I assume.
As far as I'm aware, it's an unsolved problem. Like not just the human
Right.
body. Like if you have an arbitrary PDE condition, like parameter, getting an arbitrary getting a closed form solution for the Green's function, as far as I'm aware, is like an I'm not gonna say an unsolved problem. I'm not deep enough into mathematics to know if it's unsolved or not. But as far as I'm aware, it's still an open problem. Like it's really, really hard. Like even if you have like a basic non-symmetric scatterer, like if you had like some sort of convex or concave shape, and with just a constant wave number,
Mm.
trying to get a green solution for that, as far as I'm aware, is also not solved yet.
Right. If the boundary of your jump dips in, then you're already.
Yeah, I mean, even I think convex shapes might be easier because they're convex, but I don't even know if those are necessarily solved because the corners, like, you get like reflections and scatterings, and if you're doing like, especially if your wave is strong enough, you can get like second or third order scatterings. So
Right.
like, it's actually really, really difficult.
Right.
Um,
So when you said you got rid of the greens function and replaced it with a learnable element, You said you were
Mhm.
you were losing this exactness, um, but you're not really losing anything because we don't know the Green's function for these complex
Yeah,
cases
yeah.
anyway. So,
No, no,
we're actually just
exactly.
we're getting more flexibility and not really losing anything practically.
Yeah, like if you're doing a free space, then maybe you should just use the FMM. But if you're doing any non-trivial, like heterogeneous PDE, then yeah, then we're not really losing anything.
I see.
Um,
So free space would be like when the speed of sound doesn't change, and
yeah,
then it's easier to use the FMM because it's easier to know the Green's function.
yeah. Well, you have the Green's function is like well known.
Okay, okay,
Um,
okay, cool.
if you're ever interested, you can go look at the Wikipedia for known Green's functions. There's about 50, and that's about it.
Okay, I assume if you figure out a new one, you get a big prize.
I mean, maybe. I'm not 100% sure, but like, you probably definitely get like maybe not a Fields Medal, but you probably get a professorship for sure. Like, I think if you discover a new Greens function for something interesting, you probably get a good cozy position. If you discover a Greens function equivalent for the Navier-Stokes equation, then you do get a big prize. But um, yeah, that's a side tangent for another time.
So could you apply your architecture and then look at the learned Green's function and thereby discover a new Green's function?
In theory, um, obviously the issue will be that you have a lifting function and a projecting function. So what the
Right.
features correspond to, who knows? Um,
So by lifting function, you mean like you lift to a different space that
yeah.
enables.
So yes, if you have like so let's say you have the so let's say you have uh, a function as your input, right? So you have the function value f of x, and then you have the spatial coordinates, so x and y is considered two problem. So you have f, x, and y. That's three-dimensional. And as anyone who's in machine learning knows, that machine learning doesn't really work for low dimensions at all. Um, so you need to like lift it up to some high dimensional feature space to let your machine learning do stuff.
Mm.
Um, so like that lifting function is nonlinear because it's like a two-layer MLP. So like I think yeah that like in the future there will probably be some really interesting work, maybe not on my exact thing, but like maybe someone's doing something similar or in the future, or who knows. But like there is some interesting work where you could like reconstruct the Green's function, as long as you like use some fixed input features. So if you use like some fixed known embeddings, like a Fourier embedding or anything like that, maybe you could reconstruct like the Fourier representation of it. I think it's hard because especially we can get into it later if you want, but like I use attention a little bit, and so reconstructing what the attention looks like that'll be quite difficult. But like,
Mm.
yeah, you can kind of do an inverse kernel trick and try and reconstruct what the kernel, or at least what the approximation to the kernel looks like for sure.
Okay. So let's move on to the results in your paper. So did this architecture you came up with, did it successfully learn how to propagate waves?
Yeah, it does actually. Not only that, if you go look at it, whenever I publish it, but I sent it to you. But whenever I publish it somewhere that people can actually go read it, I actually have a really nice figure where we start with effectively noise on the initialized epoch, and within 6 epochs we get like a full-on wave structure for the entire domain, like without any finagling, like it just sort of comes straight out.
Sorry, can you
So
explain that again? I didn't quite follow.
sorry. So on my in my paper, I visualize. So I take basically a screenshot of the validation image every single time.
So the
Um,
validation image is the image calculated by a numerical PDE solver.
yeah. So I have a validation set, and I visualize, and just as a gut check, I visualize the validation image. The validation set for me is constructed only of uniform images, so I can visualize them.
Mhm.
Um, and I visualized like 4 of those per epoch. And so you can sort of see how the model like learns like visually. Like obviously you can see the graphs and everything as well, but you can sort of see exactly like, okay, in epoch 1, it knows the point sources here. In epoch 2, it's sort of learning like some scattering features in the domain, and then it goes from there. But what happens that I find really interesting is in my architecture, when trying to solve like the Helmholtz equation, what happens is we go from effectively random noise at initialization, to the like a low resolution or low frequency version of the solution within 60 box, like without no encoding or anything, just like straight up learning. And we get like really nice like structure directly out immediately, which is quite nice. The same sort of thing happens for like the Darcy flow examples we use as well, where we sort of get the you can sort of see the solution, like the free you can see the free space solution coming out and then starting to convolve or like be attenuated by the differences in conductivity of the materials. But you can really sort of see this like resolving, which like you sometimes get in the FNO, but like isn't always necessarily true. Like you don't always get like such a clean, uniform updating of the entire like solution all at once. So
Right.
you do get some nice features from my result, and we also beat the benchmarks and baselines in the high frequency problems, which is like
Wow.
I guess what we tried to do.
That's awesome. So it just took 2 years.
Yeah, yeah, it was so much fun. Yeah, no, it took a while, but like it's satisfying. Like it was tough, but it was nice. Like when I finally started getting the like good clear results, I was like, okay, cool, phew. Like the I'm not gonna have to like write up a negative result the PhD thesis and explain why or explain how everything we did didn't work, as opposed to it works. Look at the nice pretty pictures. So it was definitely a big sense of relief.
Explaining that it didn't work is actually much harder than explaining that it did work.
Yeah,
It's a lot more work. Well, I think it's a huge achievement to have like beaten state of the art in such a fundamental problem. I think it's super cool. You should be super proud of yourself.
thanks. I will be when I'm done. Or published, whichever happens first, I guess.
Yeah.
But yeah, no, I'm well happy. Newer versions I've sort of been building have get an order of at least an order of magnitude better, if not two orders of magnitude better. Specifically
Wow.
in these wave problems, which is pretty cool.
Wow. Okay.
Yeah, if I had more time, I'd do time propagating problems, but those are a little harder. And well, they're more memory intensive. They're not necessarily harder.
Is there like internships you want to mention or um
Um, I mean, I did one, but it's not super related to my field.
where was it?
There's a company that did like pipeline modeling originally for oil and gas, but when I was there, they were trying to transition into carbon capture and storage. So doing the pipeline modeling for that. And CO2 is very nasty to work with. Or not necessarily nasty to work with, but like at high pressures and
Mm.
long running operating times outside, it can get quite annoying. And so the sort of stuff I was doing was like a regression problem to try learn some like parameters on the fly. But it was a good time, and I enjoyed the people I worked with. But it wasn't super related to what I was doing. At least at the time. I think now I could probably tie it more together with neural operators. But at the when I started it, I was like only a year into my PhD, so I was still pretty new at all this sort of stuff.
So do you think neural operators are going to become more popular over time? It sounds like they've got some pretty cool advantages.
I think so. Like I guess the way I think about it is that for basically all of computing history up until maybe 2018, most supercomputers were used to do physical modeling, right? Either universe simulations or I think the biggest supercomputer in the world is in the US, and they're basically doing like modeling of like how the nuclear warheads may have decayed.
Yeah.
So
Yeah.
like so physical modeling is like weather again. So physical modeling is like basically been where the majority of our compute has been historically. Um, you know, who knows where AI will go? I'm not an oracle, so like, but I guess in the worst case, if this is a bubble and like compute costs of LLMs never really go down, like I still think they'll be useful. But I think the like if you had to pay £30 for like a 10-minute chat with any LLM, I think people would stop using LLMs very quickly. Um, but so I guess like on the worst case, I think they're there where machine learning research might pivot until we get a big next breakthrough in AGI. And in the worst case, I think that they'll basically still be used to solve like inverse problems and like be cheaper methods of solving forward problems. Like I guess think about what if you could have a really high resolution or a really good approximation to a high resolution like numerical solver at your fingertips for like think like you could do a lot of work in engineering because instead of having to like choose something that was like robust because you don't know what the operating parameters would be, you could then actually maybe approximate what the operating parameters would be. So like I think there is like a big, regardless of which way the rest of the AI industry turns, I think neural operators will still have a place, and I think hopefully a big important one.
And then like on the reliability side, like you can of course evaluate uh, against the numerical solver or even the real world whether your neural operator is coming up with the right is solving the PDE correctly. But
Mm.
can you get any kind of mathematical bounds like you can for numerical methods on the error rates of your solution?
I've not found any. I've seen some people. So like the neural operator research world is sort of like quite small, but broadly split into two camps. You have the people who are doing architectures, which is where I
Hmm.
am, and then you have the people who are doing like all the theory. And as is the case for most machine learning, the theory is lagging far behind the engineering.
Hmm.
So the theory is like discussing like Bannon spaces and spaces with like specific kinds of norms and like good approximations for spaces learned by like MLPs, whatever. But the issue is that okay, there's technical reason as to why I think this is difficult. Is that how do you define what a distribution of data looks like for a PDE, right? Like if you have like if you have like a classifier or maybe a more traditional regressing problem where you have like a population sample of people, for example, like there are pretty nice statistical bounds you can put on like what you expect for the like average groups and stuff like that.
Mm.
So you can kind of like roughly define what a distribution should look like, and then you can correctly sample and get a good trained distribution. But as far as I'm aware, I didn't know how you do that for PDE. Like if you're varying the speed of sound, like how many speed of sounds do I need? How many port granularity do I need to train them on? Like how many like I guess the problem is like in my mind bigger because you have the interpolation problem from uniform grids or from either point clouds or variable resolutions. So you have that sort of like interpolation error, and then you also have the actual error of the like operator itself. And these are both really like tightly coupled because there's kind of like I'm sure there's ways you can decouple them or at least like sort of spread them apart a little bit to like gauge both of them, but like it's difficult. So like I think it's primarily just like how do you define what is a good distribution and how do you
Mm.
define what's in distribution out of distribution?
I mean, even if the distribution was like the average person's body or selecting a body at random, then like most people wouldn't really want a machine that's guaranteed to work on average for the population and want to guarantee for themselves. Like, this
Yeah,
is
exactly.
99.99% accurate on you.
Especially because like the human body is full. I think it's a house quote, but like the human body is full of like red bumps, right? Like there's so many red bumps that you have like little fat like nodules and like just tissue, whatever. Like so, the human body, every person's unique, and you're dealing
Mm.
like if you're doing acoustics, for example, like the ultrasonic stuff that I'm sort of doing, you're literally dealing with high frequency stuff. So you don't even get the benefit machine learning does of like regularizing and just assuming you can learn like a low data manifold. Like you're specifically trying to learn high frequency solutions. So like it's just a difficult domain to sort of like I think it's just very difficult domain to get good accuracy or to even really know how to even start measuring like obviously you can measure, as you said, like the direct error, but how do you
Mhm.
know whether that's in distribution and what does in distribution even mean for like even if you know the human body is for like wave propagation in a box, like how many different kinds of speed of sound maps do I need to have to be in distribution?
Yeah, yeah, yeah. Okay, well, hopefully they just get good enough that over time we're like, yeah, well, it's producing the correct answer for hundreds of people in a row, so we'll just go with it.
I mean that will probably be the marker, but
Just trust them like we trust people.
I feel like we generally have a higher bar of trust for doctors than we do for most other people, though. So like I'd hope that this is like, and because things would be like used for medical tools, I would hope this sort of would transfer through. Like I think these
Mm,
problems will be solved because like physical simulation, physical modeling is like a big industry. It's not like even if there aren't enough players in there, like lots of big companies use them. Like Boeing uses them whenever they design a plane. They model their plane in CAD and then put it in a fluid simulator before they get as the rapid prototyping before they get the model in the air tunnel.
mm.
Um, so like yeah, like I think there'll be money behind it. Um, like even in a more practical sense, like if you have an AGI, it's automating science. Like I had to do experiments at some point, and like reality is the only arbitrary truth when it comes to science. So like, hopefully these things will get better. Regardless, I just think it's a hard problem because like we don't even have like the math like yeah, it's a hard problem because we don't even have the mathematical underpinnings to understand it, and unlike a lot of other machine learning disciplines, like this is a mathematical discipline because the domain is PDE solving. So like we don't
Mm.
even like we like in a unique sense, so we kind of know what we don't know, and we kind of know that these things are actually really hard to solve. Um, but yeah, I unsure how it will pan out in the future. I hope it works out well.
Yeah, the applications sound really exciting. So I think it's a super fun space to watch, and I've enjoyed chatting about it with you and learning about neural operators. So th thanks for coming on, Emilio.
Of course, thanks for having me.